Let's see. Oh, whoops, that's not you guys. That's my honors. Bump that. And then, no, I know each last 2 days I showed you guys this, but I want to keep reminding you guys. Do you guys are you guys in your planner starting to create a space and time to study for your exams? Right? Because your AP exams are coming in about 5 weeks. I remember, guys, I got all these practice questions you could do. I mean, you could sit here for days. So yeah, there you go. There's lots of resources there. All right, let's get going on. Let's start with nuclear engineering. Okay. And try to go kind of fast. I think I can fit everything in today. Got these 2 things. All right. Oh, you're looking at this is 1946. So the year after the Second World War ended and the year before the Cold War officially started. Yeah, 1 year of peace. That's what we did. Boom. Okay, that didn't look like peace, but that is a representation. So let's start the story. Let's go about 100 years ago when these guys discovered the neutron. Right. So you guys have neutrons, kind of like you guys have protons, neutrons, electrons, right? Now it turns out that electrons are fundamental particles, but protons and neutrons are not. You actually break this down to subatomic particles called quarks. Looks like 1 up quark and 2 down quarks. There you go, a little technical stuff. Then 1930s, these 2 scientists, German scientists and Austrian scientists, Lisa Meitner and Otto Hahn, realized that if you take, this is supposed to be representing a neutron up here, if you bombard a uranium-235 atom with a neutron, it will actually create a nuclear reaction. This was like the first nuclear reaction that was run in a laboratory. This is one example of a nuclear reaction. You can break this into krypton and barium, and then, oh, look at that, it releases 3 more neutrons, which then could bombard more uranium atoms. Hey, this could like set off like a chain reaction process, couldn't it? Now, I'll tell you guys that isotope of uranium, U-235, you guys know from chemistry, different isotopes have different numbers of neutrons, right? This is the not very common isotope of uranium. The most common one is U-238. That one's not super interesting. You can't really run nuclear reactions with that, but U-235 you can. We'll come back to that. Right now, what's the deal with the nuclear reactions and how are these different from chemical reactions? You guys remember in chemistry, you learned that conservation of mass, right? And if you add up all the mass of the reactants and all the mass of the products after some chemical reaction, it has to equate. That's not exactly true for nuclear reactions. Nuclear reaction, it looks like there's going to be missing mass, but it doesn't disappear from the universe. It converts into energy back. Remember this right here, E equals mc squared. Right, so take some mass, multiply it by the speed of light squared, and you get the equivalent amount of energy. And so you're going from kilograms to joules. And how about each of these graphs? How do these align with these? Now both these graphs are the same idea, just different points of view. The left one is mass per nucleon, the right one is binding energy per nucleon. So either mass in terms of energy. We got all the elements listed left to right. So going from hydrogen up to, well, the largest natural element in our solar system is element number 92, which is uranium. More on that story later, but if you ask the question like, well, what is the mass of a nucleon? That's to say either a proton or a neutron, just to use the left graph. Okay? Then actually it depends what element you're in. So in hydrogen, the mass of a proton or a neutron is heavier than other elements. It decreases until you get to iron, and then it increases after that. So why the mass difference? Well, one perspective is that it takes more and more energy to bind those nuclei together until you get to iron, and then gets less after that. And there's this trade-off between mass and energy equivalence. Right? All right, so there's going to be 2 halves of the story. There's going to be a fission half and a fusion half. Fission is taking these heavy elements like uranium and breaking them apart into smaller elements. And then, there's going to be missing mass. See, if you break element into smaller elements, there's going to be a decrease in the mass, which gets converted into energy. Or if you look at binding energy, similar idea, right? And then later on, near the end of this presentation, we'll look at fusion, which is if you take hydrogen and fuse that into helium, that's like the energy of the sun, right? Do you guys see a much greater drop there? Ooh, I bet there's like almost 1,000 times the energy associated with that type of reaction. Right? Okay. Now, if you have iron, that's no good for a nuclear reaction because you can only lose energy running a nuclear reaction if you start with iron, right? So iron's kind of. Right, here's the Chicago Pile. The first nuclear reactor was built at University of Chicago. during World War II as part of the Manhattan Project, which you guys know from history. That was the U.S. government was funding this atomic research. We were trying to beat the Axis powers to creating the nuclear, creating an atomic bomb. So scientists knew that in principle nuclear weapons could be created. Convinced the government, hey, let's pump money into this research project, Manhattan Project. Right, so the first like fully uncontrolled fission reaction was created 1945. This is Trinity Site, New Mexico. You can actually go and visit the site to this day. I know because I remember I went there as a kid, and people who work there, like as their day job, they have to wear these special suits, probably lined with lead or something to keep from getting contaminated with radiation. Now, if you're just a day visitor, just there like, like visit once or twice, then it's okay. It's, that radiation exposure is not going to really hurt you. But in 1945, and of course 1945 also, we actually used a couple of nuclear weapons in war, the only ones ever actually used in war. So how do you create this this fission reaction? Breaking apart heavy elements, and then the difference in mass will create some amount of energy. Right, so let's look at this uranium. So if you dig uranium just out of a mine like somewhere on Earth, the vast majority of it, over 99% of it, is U-238, which is not the part that we're going to use for a nuclear reaction. We need that little red sliver proportion, that U-235 isotope. Right, so you need to enrich the uranium. Now, how do you enrich the uranium? There are different methods. One method is you can vaporize the uranium, put it in a centrifuge, all the heavy stuff goes to the outside, on the U-235 goes to the inside, you can extract it from there. Now, if you can up that percentage, if you can enrich it to about 3 or 4%, that's called reactor grade uranium. Talk about that a few slides from now, where you can use this for nuclear energy, right? So you can run a controlled reaction and create energy on the grid. If you can up that proportion to 90%, you get weapons grade uranium, where that's like this picture on the left side here. Right? This is weapons grade U-235. And then once you have this, it's actually very easy to create an atomic bomb. So you just actually, that's the slide right here. Right? Yeah, you guys aren't gonna go home and create nuclear warheads. I know you guys are too responsible for that. So here, I'll show you guys how to make one. Right, so just take some U-235. Blasted at a critical speed at some more U-235, and boom, then that will initiate a nuclear reaction, and you'll get all that energy back very quickly. Right, so the two bombs that we dropped on Japan at the end of World War II were actually different categories of bombs, and they were both fission bombs. But the first one we dropped on Hiroshima was from U-235, just like I showed you last few slides. Actually, this was completely experimental. This was the very first of its kind. It was an entirely experimental bomb. Now, we had detonated nuclear bomb in New Mexico at Trinity Site, like I said, but that was actually a plutonium bomb, like the one we dropped eventually on Nagasaki. Plutonium is actually element number 94 on the periodic table. There is no natural plutonium anywhere in our solar system. Which links to the question, like, where do the elements even come from? Probably what happened was 4.5 billion years ago, there was some supernova event, some star went supernova. Possibly our sun is one of the main theories. Our sun might be like a second or third generation star that has exploded once or twice before. And from supernova, you get all the elements beyond like hydrogen and helium. Hydrogen and helium you get from the Big Bang. Right? So, but then the size of that supernova determines the largest elements that you have within a solar system. And whatever created our solar system, it only goes up to element number 92. But there are stable elements beyond that, like plutonium 94. All the plutonium we have in our environment now has only existed since 1945, since we've been running nuclear reactions. So fun facts. All right. Has some video not playing. I think we can. I think we'll be all right. Let's skip that. All right. So we were able to actually control a fission reaction to actually create nuclear power plants. Depends what number you're looking at. Possibly as far back as like 1951. So these are all American technologies, by the way. And then the Soviet Union was like a few steps behind us. There are different, this gets more into the engineering, different types of reactors that you can take. The most popular one you guys see here is a pressurized water reactor. Let's take a look at this. Do you guys remember I was showing you guys the Rankine cycle in the last couple of days to create, to generate electricity? So that's a lot of all the blue stuff is like water being cycled around through this Rankine process. This is how you get, even from coal, you can get energy like this, right? So you boil water, that turns a turbine that also forces wires past magnets. That's what a generator is. We'll create a motor in this class probably in a week or two. So it's just the opposite process of a generator, right? To turn mechanical energy into electric energy, then that's how you get well, the electricity on the grid, right? But how about the actual reactor part for this nuclear reaction, right? Well, like I said, there are these different designs you can create. To simplify, I know that's kind of a long list of different reactor types, but to simplify this a bit, let's say you have two categories of reactors. You can either go like a high pressure or high temperature. And the one we went with was high pressure. And then for most of these reactor types. Also, something that could possibly be involved in reactor type, depending on your category reactor type, is something called heavy water. If you guys ever hear this term, heavy water, heavy water is created with and isotopes of hydrogen, because you guys know water is H2O, right? But if you use isotopes of hydrogen that have neutrons in them, right? Because most hydrogen is just a proton and an electron, but you can have one or two neutrons possibly in hydrogen too. Then you can create water that's actually more dense than regular water. And this is useful for slowing down neutrons enough to help to create a controlled reaction so that it can run a nuclear process. Right? But it's not the only, you don't necessarily need heavy water. There are other types. You guys see this purple one says LWGR. That LW stands for light water, like a light water reactor. So those are possible too, in different designs. Let's look at electricity used on the electric grid. So here's us right here, United States, 20%. And the United States has three main electricity grids. There's basically east of the Mississippi, west of the Mississippi, and Texas. And it's kind of like one giant grid each, but about 20%. So what's running the air conditioning in this room, or that projection, or when you guys charge your phones, you're getting approximately 20% of your electricity from nuclear reactions, right? From uranium, right? or plutonium possibly, right? So here's a power plants created by year, mid 1950s. The first ones were built for actual like commercial use. More and more were built until, well, okay, I think this is worldwide. I want to say in the States, you need to fact check this, that we haven't really built any or almost none since 1970s. You guys see a couple of events here, these nuclear disasters that happen. The one's not on here, of course, is Fukushima, 2011 off this chart. Right, so nuclear power has huge upsides and also huge downsides when things go wrong, right? So the huge upsides are you get an enormous amount of energy from nuclear, right? Just a small amount of material, 20% of the electricity on a grid array. Oh yeah, whoops, I forgot some detail. Let me scroll back. I wanted to point out that France actually famously gets 75% of their electricity on the grid from nuclear. And there are only a handful of countries, I think it's like 8 countries that have nuclear weapons. And ironically, 3 of them are down here at the bottom of this list, India, Pakistan, China, have hardly any power plants for electricity consumption. But all right, so huge upsides and huge downsides to nuclear if things go wrong. Nuclear is considered to be clean energy in the sense that it doesn't create greenhouse gas emissions, so it doesn't really add to climate change or global warming. But of course, you have this nuclear material that you have to store for like tens of thousands of years, right? All right, now here's where to put a twist in the story. You guys see this molten salt reactor? So this is just a different design reactor. Do you guys see this freeze plug right here? This freeze plug? Now this type of reactor is a high temperature reactor in contrast to the high pressure that most reactors are. Now those high pressure reactors, you have to constantly monitor them and make sure they're cooled. And I don't know if you guys ever watched that HBO documentary series, Chernobyl. Right, they were showing like what went wrong and eventually caused the meltdown. And you guys know Chernobyl is in modern day Ukraine, old Soviet Union back in the day. But that high pressure reactors are dangerous in the sense that you got to monitor them, make sure that temperatures don't overrun, the thing goes into meltdown, get an uncontrolled nuclear process. But if you have a high temperature, like molten salt reactor design, then if things go awry, then what happens is that this freeze plug gets melted. All your nuclear material gets dumped into these emergency dump tanks, and then the reaction just like dead stops, like a much safer design, right? This has passive safety, like walkaway safety. so that something happened, like all your engineers, like, I don't know, strike or die or go away or don't show up to work, then the process just shuts down. You don't end up with a meltdown. Now, thing is though, that type of reactor actually involves a different fuel source called thorium. You guys may have heard of this. There are proponents of using thorium over uranium. And well, here's all the some of the main points for this. One is that thorium is a lot more abundant than uranium, so the fuel would last longer. Now, there is nuclear waste, but very little nuclear waste compared to what uranium produces, like less than 1%. Also, the half-life of this nuclear waste is not nearly as long. So if you look at the products of nuclear waste, for uranium, it lasts tens of thousands of years. And one of the problems is, like, how do you communicate with people tens of thousands of years from now that, like, oh, avoid this site, we've got this dangerous nuclear waste. But for thorium, the products you get only last like a few hundred years. Yeah, now this would be involved with that molten design reactor. And the reason is that you actually need a little bit of uranium to kickstart the process. So like you need one fuel source to initiate the other. So that things go awry, it'd be very easy to cut off those two different fuel sources from each other, and then the extra thorium will just that reaction will just come to a stop. Now, why aren't we using these thorium reactors? Well, one probable reason is that thorium is not useful in creating nuclear weapons. So if you roll back the clock, let's say it's like 1950s when you have the government funding like billions of dollars of nuclear technology funding. Say, okay, well, what technology do we want to fund? They had to pick, do we want to go with high pressure or high temperature reactors? Do we want to go with uranium or thorium? And so, well, we do want our common knowledge base, our nuclear scientists, to understand how to create nuclear weapons. We were in a Cold War back in the day, so they went with uranium, and you'd have to have this design change to switch over. But those are proponents of thorium would say those things. All right. Let's switch over and look at the other half of the story, fusion. Because if you look at the like the height change on this graph going from uranium to the reactors to the products, okay, there's a small height change, which means small change in mass, which means it is an enormous amount of energy. But there's a huge drop here. It's roughly order of magnitude of like a 1,000 times as much, or like hundreds of times as much. Right, so I'm gonna get into fusion. Right, so the first uncontrolled fusion reaction was created. This is the first hydrogen bomb, 1952. So okay, well, at least a man-made one that I'm talking about, because the sun is actually a giant fusion reactor, right? You have hydrogen fusing into helium. Okay, here's what that looks like, a fusion reaction. And I think I may have had a picture or video of a hydrogen bomb. It's just not showing up on the presentation, so oops. But anyway, a hydrogen bomb is almost 1,000 times as powerful as the type bombs that we dropped on Japan at the end of World War II. Right, so, here's how you create a hydrogen bomb. You actually it's composite bombs. You actually do start with a regular fission bomb to kick off the fusion process. So it's like one detonates the other. Right. The largest fusion bomb that was ever detonated was by the Soviet Union. But let's see what we got here. But can you control a fusion reaction to actually generate electricity on the grid? Right now, this is one of the biggest uncracked problems in science and engineering. So we haven't cracked this one yet. But once we do, then this will solve so many problems in terms of energy source or clean energy or climate change, because the fuel source you need for this is just deuterium, so special isotope of hydrogen that is extremely abundant in seawater, right? So you could just use seawater and it would basically never run out. Here's Lawrence Livermore laboratory where they're trying to crack this problem outside San Francisco. Here's a lot of the fusion reactors look like this, take this type shape. Right, here's fusion reactor. There's they always say like fusion is like 20 years away, like 1980, how far away from fusion? 20 years. 2000, how far away? 20 years. Recently I heard a recent Secretary of Energy say that we might actually be close to like 10 years away from developing fusion. There was this, okay, here's part of a science article, copy pasted here. There was a recent breakthrough, but they got a lot closer. We actually can create fusion. They have done this. The problem right now is that it's not economical. So the amount of energy that you put into the process is more than the amount of energy that we're getting out, but we're getting closer, right? So possibly soon. Okay, fusion, fusing these isotopes of hydrogen and helium, getting lots and lots of energy out. And this would basically, I mean, it would just be so abundant, it would last so long. All right, so yeah, I gave you guys a kind of a fast version of that, but we'll switch over and look at civil engineering. Civil engineering. Okay, present. All right, so let me do this.